Thank you very much to the organizers. It's great to be here. Enjoyed Cambridge quite a lot. So I apologize to those who I gave a very similar talk here a month ago, so some of you have heard it. It's slightly different than that, but essentially the same. And I also gave a very similar talk a couple of weeks ago in Vienna, and a number of people who are here were there. So, well, on the other hand, I know for myself that I don't actually mind hearing the same thing more than once. But maybe that's more of a comment on me than you. So, okay, and before I go further, let me mention the papers that I'm talking about. So, so there are two papers on the archive. One from last year and one that was recently posted. I seem to get work done in June. Okay. And this last one is joint with Jörg Fröhlich. Okay. And actually, that's the one that I'm going to focus on the most, although I'll describe also, to a certain extent, the results in the other paper. So the concern of this work is the following. Consider a system that we've been talking about all day, namely the Anderson model, in the large disorder regime, in which we know by many different methods now that we have localized spectrum, that we have pure point spectrum, and we have dynamical localization in particular. And now consider small perturbations of this system in which there's some sort of time-dependent noise. Either simply the most naive thing to do is to add a time-dependent random potential to it that fluctuates stochastically in time, or couple the system to a heat bath, the particle to a heat bath, so that it experiences some sort of quantum noise. And then the expectation is that the Anderson localization should be unstable under that perturbation, because essentially the particle is continually getting kicks, either from the heat bath or just from the classical noise that we've hit it with. And as long as those kicks are in some way independent of what you've seen in the past, then the sort of general philosophy of the central limit theorem suggests that you should have diffusive motion for the particle in the long time limit. And actually this is somewhat related to random walk in a random environment, where of course there are some results known, as we heard yesterday, but this is actually more closely related to the older results about random walk in a random environment, in which there's some sort of detailed balance which allows you to say a great deal more, and it's easier than what Bolthausen talked about yesterday. So, so let me actually write something on the board. So the context is the Anderson model. So let's start with that. So in particular, I'm going to be focusing on the time-dependent Schrodinger equation, because ultimately it's a time-dependent problem that I'm interested in. So we consider the time-dependent Schrodinger equation with H omega, our favorite random Schrodinger operator, which we can write as follows. So it's the same operator that Abel and Alex talked about. Okay. And the omega x, you can think to yourself, well, I mean, at minimum, I want these to be a stationary random field. In fact, I'm not going to use very much about the distribution of the omega x's, except I would like to assume that we've proved localization by some means. And of course, to prove that, you might like the hypothesis that you have, say, independently identically distributed random variables with a nice distribution. maybe, for instance, Holder continuous, or even just a bounded density. Okay, so that's, now of course it's well known that one has the following theorem, and I'm going to, well, that, and oh, I should say, where does this guy live? This guy lives on L2 on ZD. So, and I have two parameters here, U, which controls the hopping strength, and lambda, which controls the disorder strength. Of course, that's more parameters than I need, since an overall scaling factor is not terribly important. But I'm going to introduce another parameter later. Anyway, actually probably don't need both those parameters. But. So there's a constant, kappa, which depends upon the dimension and the distribution, rho, such that if U over lambda is less than kappa, then localization holds. Okay? Now, for the purposes of this talk, localization is going to be something much more elementary than what we've seen this morning. I'm going to write down what Anderson originally was referred to in his paper in 1958, which is the absence of diffusion, because I'm going to say something about diffusion for a perturbation of the system in a bit. So what I want to say is that the following, if I sum over x the expectation value of the x0 matrix element modulus squared of the unitary propagator. So this is the mean squared position of the particle at time t, mean in the sense of both quantum mechanics and averaging with respect to the disorder. And this quantity, which I choose to normalize by the dimension, just because there are d terms contributing to the sum of x squared, is finite. Okay, so this is a bit stronger than absence of diffusion, right? Diffusive propagation would be the situation where if I divided by t here, I had a limit. That would be diffusive scaling in the long time limit. And the point of localization is that this L squared, L stands for localization length, is finite. Okay, so as long as the disorder strength is large or the hopping strength is small, we have a finite localization length. And this is well known, and it follows from exponential localization. And of course, it's known that in fact exponential localization holds in the same regime. So in fact, right, this is actually bounded by a constant. I can get rid of the one since it's the unitary. So in fact, we have that, right? At least for nice distributions, although one could imagine there being other stationary random fields where you could prove this to be finite without proving the exponential decay. So, so this is going to be for me an assumption that we simply have this. Okay, and now I want to move forward and consider what happens when we perturb the particle's evolution.
That's going to be the only input you need.
That's basically the only. I want stationary random fields. So at some point I need, the fact that the distribution of omega of x looks the same at every point. And in fact, it doesn't really have to be a random field. This could be a quasi-periodic type thing, as long as I have this input. That's all that I will need from the random Schrodinger operator theory. Okay, so now let me say a word about what the problem that one really should solve and that I'm not going to solve. So the most natural problem from the standpoint of physics is the following. let's introduce an auxiliary Hilbert space, which is the Hilbert space of the heat bath that we want to couple the system to. So we're going to consider a Hilbert space which is L2 of ZD. And now when I introduce an auxiliary Hilbert space, I'm considering now an open quantum system. I have my particle and it's interacting with something. I need to introduce the other system as a tensor product. And so there's another Hilbert space here, which I'll just label as H bath for the heat bath. And the heat bath has some Hamiltonian on it, which I don't want to get into the details because I'm not going to actually solve this problem for you here. But what you should do is, for instance, consider a bosonic field with, say, free bosons here. And so you could consider now a Hamiltonian on the whole system, which is the random Schrodinger operator, tensor the identity, plus the identity on L2 of ZD, tensor whatever the Hamiltonian is here, plus some interaction term. And the kind of interaction term that it is somewhat natural to consider is, for instance, something like this, if you know what I mean by that term. If you don't know anything about sort of the Gaussian quantum fields, then just never mind. Just assume there's some coupling between the system. And this is a tensor problem. Okay, and now one would like to consider the long time behavior of this with a particular state for the heat bath. For instance, one might like to consider a thermal state for H, or a KMS state. So formally, in order to do that, we have to be taking a thermodynamic limit, or choosing the right representation for this bath, in which case we can consider that just to be a vector state. And one would like to start, for instance, we start the system in the state where the particle is localized at the origin, and the heat bath is in this state rho beta. Beta here would be the inverse temperature. And we would like to consider the evolution of this state. And in particular, we don't really care about the heat bath. We don't really care what's happening to the heat bath. What we care about is what happens to the particle. And one would like to consider the following, which is we're going to evolve the state according to the Schrodinger evolution. I'm using a density matrix on the, it's not a pure state on the system, and so I'm using the evolution of the density matrix to describe the system, and now we can trace out the heat bath. So we trace out over, take a partial trace over the heat bath, and we will call this, let's call this R beta. Because R will not appear again, and rho will. We'll call this rho t. It always annoys me when I see rho beta and rho t, and I know that they're different, but I think to myself, what if beta equals t? And okay, so that's okay. So one should consider this, and one should consider the long time limit of the limit as t goes to infinity of the sum over x squared x rho t x divided by t. And the conjecture would be, under suitable hypotheses for the heat bath, that this that this converges to a finite positive limit. Actually, quite generally, as soon as you allow the particle to interact with a heat bath, diffusive propagation should emerge. Okay. So this is really the problem that one ought to solve, but it's technically rather complicated and hard to make progress on.
Jeff,
Yes?
when you say you expect this to be generally true, is it important that you take Anderson model, or you can pick something else?
Anything, as long as, right, it doesn't even really matter that it's stationary, as long as the system, obviously if I put a trapping potential in, then you don't expect this to happen, okay? So I need some sort of homogeneity in space in the sense that the particle is free to evolve off to infinity without having its energy grow, right? But once you have that, the heat bath, as long as you have some sort of homogeneity in space, what's happening is it keeps getting kicked by the heat bath, and presumably the heat bath keeps dissipating off whatever. The recurrence is not terribly important because the heat bath has the ability to dissipate energy off to infinity. And so although the particle interacts multiple times with the heat bath, after many, many interactions, you expect there to be low correlation. Okay, so I'm not claiming I know how to prove this at all. This is pure philosophy. Okay, but yes, I expect very generally, if you do this coupling, that and you make a good heat bath Hamiltonian, which I haven't described, that you should just get diffusive propagation. Okay, and this should be associated with a central limit theorem for this is just one observable, and actually, if I look at the full distribution of the position of the particle, maybe I want to average here. Probably that doesn't matter either. The full distribution of the particle should be Gaussian. Okay, so now I'm not going to solve this problem, okay? So I just want to put that up there as a natural problem and something that it's worth spending some time thinking about, although I don't think it's terribly easy, but it's probably not the hardest problem out there. So, okay, now there's a natural sort of approach that's taken in the physics literature to such problems, which is the so-called Markov approximation, in which there are a number of ways to derive it. I'm not going to go through that, but basically one makes an approximation where you assume that rho t itself satisfies a closed form equation, and then you figure out what sort of equation it does satisfy. And these things actually become exactly correct in a suitable limit in which you take a long time limit and you take the coupling constant g to be small and take a kinetic limit, it's g squared over t is, or g squared t is constant. Okay, so, but I'm not going to concern myself with that kinetic limit. The theory of that actually goes back to the 70s. Davies worked this out, at least for finite systems with a decent gaps in their spectrum. It's a little unclear whether it works here properly, but this actually is a situation where you might be able to work out the kinetic limit. I actually just want to write down an equation. Okay, so I'm going to write down an equation for rho, which is the following. So this is what I would have for the density matrix of the particle if there were no interaction with the heat bath. It's just the commutator with h omega and an I. And there's going to be another term here, which is a so-called Lindblad generator. And so where e to the t g L is a suitable semigroup, okay, I don't want to get into the theory of this, on the set of density matrices. So on the set on the say the on the trace class operators on ZD. Okay? And this is a so-called Lindblad equation. And they're widely used to describe exactly the interaction of an open, the evolution of an open quantum system in which you have something that interacts with a heat bath. And the heat bath is taken into account here in L. Now, of course, I have to tell you something about L. And if you carefully take the kinetic limit, like I said, then, or at least formally take it, you'll get a particular expression for L. I'm actually not going to use that. I can comment a little bit on that later. It's actually still somewhat complicated. That's sort of work in progress that I think I can say something about it, but it's not the situation that I'm going to talk about today. So, so let me introduce the Lindblad generator that I'm going to consider, and then describe the results. So the Lindblad generator that I will consider is let's suppose that L is non-random, so it's not stochastic. It doesn't depend upon omega. So, which is incorrect if you take the kinetic limit I described before. Actually, you do get something that depends upon exactly the spectrum and the eigenfunctions of the random Schrodinger operator. And let's suppose that it commutes with translations, actually with lattice symmetries. Now that's correct for the thing that you get if you take the kinetic limit, although it commutes in distribution with lattice symmetry since it's random. But if I'm going to suppose it's non-random, then commuting in distribution means that it just commutes with lattice symmetries. Okay, so if I shift things around, I get the, right, if I shift or rotate or reflect, then I get the same result. Okay, and then this is not the most general form of such an operator, but it's a reasonably general form, is the following. So here's, I need to introduce some notation. So I'm going to make a sort of change of variables, which is a little bit annoying to do on the lattice, but it's possible. So essentially, capital X represents something like the center of mass of the particle, and C is, well, how far off the diagonal I'm looking at the density matrix. Okay, and so notice that X and C have to satisfy a constraint, which is that their sum has to be something which has all even components, because otherwise I can't divide by 2 and get something sensible. And so that constraint is implied throughout by the notation. Okay. And I introduced two operators here. One is called the gain operator. And the other is the loss operator, which actually just compensates okay, and the Lindblad generator is the difference of these two things.
R is some kind of kernel.
R is some kind of kernel that I'm going to discuss in a bit. So the
X is a position operator?
No, X is an element of ZD. So yeah, so the reason I used Dirac notation before is because I want to consider, I'm going to using functional notation when I use coordinates. So here, X and C are points in ZD, and they have the property that X plus C is an element of 2Z. And it's just a way of parameterizing the elements of the density matrix, which is a little bit bizarre from the standpoint of what one's used to doing here. It's actually in the continuum, it's fairly natural. This is sort of if you take a Fourier transform of C, you get what's called the Wigner transform of the density matrix.
But in this case, what do you mean by this bracket? You are not taking the expectation of rho.
That's Dirac notation.
Is the Dirac notation, but
We're in England. I'm using Dirac notation.
which are the states?
Position. Delta.
These are.
Oh, this is a delta function for him. Okay, okay,
Yeah.
okay,
Yeah.
okay,
Okay.
okay,
Sorry.
okay.
Good. So now the Lindblad generator is the sum of these two things, or actually, well, more strictly speaking, the difference. Okay, and it has the property that one can verify that the trace of L of rho is always 0. So it preserves the semi-group that it generates preserves the trace. And that's actually fairly easy to verify from these two things. Notice that the trace of rho can be expressed as the sum over capital X of rho x 0. Right? When I want to take the trace, I have to put I have to take a matrix element on the diagonal and sum over all of those. Okay, so I should say a little bit about what the meaning of this is. So R is a kernel that I haven't told you much about, but I call it the gain kernel because it's the thing that describes the gain operator. Okay, and the form that the assumptions I want to make about the gain kernel are as follows. I'll put them over here, but I should introduce some notation first. So let's look at the Fourier transform of rho and actually of the gain kernel and of rho with respect to the variable xi. So let's W of P will be the Fourier transform with respect to xi So this is the Wigner transform of the density matrix. And it's a sort of stand-in in quantum mechanics for a phase space density. It has the unfortunate property that it's not everywhere positive, and so we can't really consider it to be a density. But we can sort of consider W to represent the probability of finding the particle at position x with quasi-momentum p, except for the fact that it's not positive, or even real valued necessarily. Okay, and so if we consider the action of the Lindblad generator on W, so I'll just sort of overload the notation so that there's understood. If Lindblad's going to act on W, then I'm going to take a Fourier transform. Right, what this means is act on rho and then take the Fourier transform. Then this is the following. It's the integral over the d-dimensional torus of the Fourier transform of the gain kernel with respect to both of its variables. Okay, and now maybe things make more sense, and I'm integrating here with respect to q. So there are two variables here. It's sort of clear I have to integrate with respect to q because p appears on the other side. And in case you're curious, dq always represents normalized Haar measure for me. I want it to have mass 1, just because I don't want to write 2 pi's around. Okay, so now things might make more sense. You can sort of see what this is. If r hat's a positive measure, then this is actually just the generator of a Markov process which hops in momentum, a hopping process on the torus. And that's exactly what we want. That's exactly what's supposed to be described here. So what we're really describing is a situation where the particle is evolving in time according to the random Schrodinger evolution, but then periodically at Poisson distributed times with some weight that depends upon its momentum, the particle gets a momentum kick, and it jumps in momentum. Okay, and this is the model. And so we're going to assume certain things here. One is that the measure, this guy should be a positive measure. Now, it's not necessarily an absolutely continuous measure. In fact, we don't want it to be. A quite typical example of these is something like a delta function where E of p is the symbol of the Laplacian or something else. So a sum over something like this, and omega is some dispersion relation for the bosons that were in the heat bath. This is the kind of thing that emerges, except that at positive temperature there are some weights, at finite temperature there are some weights here that depend upon the temperature and describe detailed balance. So this is exactly the form of operator of r hat that would emerge if you did the kinetic limit calculation formally for a particle without a random potential interacting with the heat bath. Yes?
Energy or what?
Epsilon is the symbol of the discrete Laplacian, sum of the cosines. It's some, yes, it's the one particle energy. It doesn't have, this is supposed to just simply be an example. But yes, it's kinetic energy. Okay. So, but the basic thing is we want this r hat to be a positive measure, so that this has the interpretation as a hopping process, the generator of a hopping process. Key thing is that we want that hopping process to be ergodic on the torus and with exponential return to equilibrium, which is guaranteed by an estimate of the following form. Where this is an integral over both p and q. So p r hat may be a singular measure, but if I'm looking at the difference of if a difference of a function at the points p and q, I can replace it from below by an integral with respect to the Haar measure on the torus. So basically what this amounts to is, I mean, this sort of condition will hold if several convolutions of L with itself become absolutely continuous, even if r hat itself is not. In other words, if in some finite number of steps I can go from any point, it is possible to go from any point on the torus to any other point. Okay, so this is just going to be an input. We're going to assume this condition. And then finally, and this is the most so this is the most fundamental condition. It's a gap condition for the generator. It tells me something about the location of the spectrum of L, and it drives things in a clear way. This is a slightly more technical condition, which is that I need to know something about the stationary state for this Markov process. And in fact, for the analysis to go through simply, I need the stationary state to be trivial. So I need basically, if I put in one, if I put something's not right. If I put, if I have something transposed. Yes. I already did the thing that I can do if I have the condition I'm about to write down. So, in general, the entries get reversed here. What I would like to know is that if I plug in 1 here, the uniform measure on the torus for W, that is annihilated by the Lindbladian. Okay? So what I would like to know is the following, that if I integrate out either one of the variables of r hat, I get something symmetric. So this is implied if r hat is itself symmetric, but symmetry is stronger than you need for this, right? If it's symmetric under interchange of the two variables, this is actually the condition I need. And it tells me something about the stationary state for it. It tells me I know what the stationary state is. It's the uniform measure on the torus. It holds for this example. As I told you, there should be some temperature-dependent factors that sit out in front, but if you take a formal infinite temperature limit of this operator, then this holds. Okay, so, and then there's some other weak print, fine print about boundedness and continuity of certain things, which hold also in the general case. Okay, so let's write down a theorem and then describe the other example, and then say a few words about the proof. Okay, so so the theorem is the following. So let's let rho t solve the equation, and let me put the equation over here because I've covered it up. So the equation is the Schrodinger equation. Okay, and we'll call this 1. Let's solve 1. And there's a g sitting here, a coupling constant, which will appear a little bit further below. And let's take the initial condition to be a particle localized at the origin, just for simplicity, and g positive. Okay? Then the diffusion constant, which is the limit as t tends to infinity, this guy exists. The limit exists and is finite and positive. And it satisfies d of g is delta times g plus little o of g. So as g goes to 0, this is little o as g goes to 0. I'm not concerned with a large coupling limit. The thing is proportional to g, where delta is some positive finite quantity. Okay. Yes?
I would think that if g goes to 0, you, in some sense, start to approximate the dynamics of the
Yes.
operator.
Yes. So I'm assuming, right, so it's sort of, let it satisfy this, and Anderson localization holds for h omega. Okay? That's, okay? Right, so as g goes to 0, you're approximating this. The dynamics of the random Schrodinger operator itself don't have propagation. Have diffusion constant 0. Because actually this quantity is bounded uniformly as t goes to infinity, so I divide by t and it goes to 0. So that's exactly what's happening here. And in fact, we can say the following, that delta, the bound we have on delta, is there's a constructive bound on delta, which the lower bound's not so important except for to prove that it's not 0. And I can put here the localization length that I wrote down before. So actually, it's interesting. I mean, if you think about if you sort of look at this and take the right-hand side, ignoring the 1 here, to be the behavior. Wait, do I have this right? Yes. Right. Yeah. Never. So ignoring the prefactor here. So basically, what this appears like is that delta, that the diffusion constant is approximately L squared times G. L is the localization length. G is this coupling constant. And of course, this is basically what any physicist might write down as a first guess, because I've simply taken the only quantities in the problem that have the right dimensions and combined them to perform something that's the diffusion constant, right? L is the localization length at some characteristic length. G is the inverse of a time scale over which L operates. What else could the localization length be? Okay, and so at least at the level of bounds, that's what we get. Okay. Good. So now, actually, for the theorem, I can say the following, that up till here, one doesn't need anything about the random Schrodinger operator. One needs no randomness up to here. The stationary random field, the fact that the field is stationary, is important in the proof, in the technique. So one needs some sort of translation invariance, but it actually would hold here, even say for a periodic system, or for any quasi-periodic system. To get this estimate, you need the localization. So the localization really only comes here in the end.
Jeff, you prove D is strictly positive?
Yes. So in the general case, D is positive and finite. Let me go ahead and write that down. Okay. But in order to get estimates on D, one needs to know, right? You can sort of read off here, right, that this still has a nice limit as lambda goes to 0. So in the zero disorder limit, I still have an estimate on delta on the diffusion constant. Sorry, if I write down here delta G, right? But I don't have a good upper bound. In fact, if lambda is equal to 0, then the diffusion constant is equal to some constant over G. Not bounds, it's actually equal to. One can simply, one has an identity for it, and it's simply equal to a constant over G. This constant is, I can probably put, well, the constant depends upon U. I could probably put a U squared here, but it would go to 0 if the hopping strength went to 0. But so for the particle interacting with the heat bath, to the extent that that's what this is, described by just the Laplacian alone, we have diffusion, but we have diffusion with a very large diffusion constant that's proportional to 1 over G. Okay.
Question.
Yes.
Is there, would it make sense to look at some kind of conductivity for this problem, or?
I mean, that's an interesting question. At this level, so right, you want to perturb it by an electric field and look at the response. The thing is, if you do that wrong, you'll get the wrong answer. And the naive way is the wrong way. Namely, if I just add the electric field as a potential, then you can go through the calculations and discover you still get diffusion. So if I just add E dot x as a potential and look at the effect, it doesn't affect the limit. Now, physically, this seems weird. And that's because if you go and you look back at where the Lindblad came from, when you derive this, this depends upon the Hamiltonian for the particle. And actually, if you do the derivation, the Lindblad generator also changes when you add an electric field. And you need to add the correct perturbation here for the linear response. And then, in principle, you should be able to do it. But since I'm already making sort of all these sort of just simply guesses about what the Lindblad operator is, it's a little bit... I would be almost just reverse engineering it so that it worked out, because I would just simply make a perturbation. So what one really ought to do is derive the Lindblad generator in some rigorous way, or semi-rigorous way, and do it in the presence of an electric field, and compute the linear response there. So yes and no. In principle,
I'm thinking of like a DC conductivity, like a,
or, I mean, of course, if I just want to appeal to the Einstein relations and do physics, then of course I have the diffusion constant, and Einstein told us how to write down conductivity from that. But again, that's more or less defining the answer to be what I want it to be. So,
okay, well, anyway, we can
yeah, we should, yeah. Okay, so let me describe something about the other paper, and then I've gone so slowly, I think I won't have time to say much about the proof. But maybe it's better just to describe the results. I don't know. I'll say something about the proof, because this won't take that long. So a similar calculation can be applied to the following problem. Where actually I don't have to use the density matrix to set the problem up. So I can consider the random Schrodinger operator, and I can perturb it by a time-dependent random potential. So here, Vx, so this is going to be equation 2. Vx is a stationary random field on a probability space, sigma nu. Sigma is the probability space. And T goes to sigma of T is a Markov process on this space with invariant measure Okay? So in other words, what I'm doing is I'm taking the random Schrodinger operator and I'm adding to the potential a small fluctuating piece, right, which is fluctuating stochastically in time. Okay? And if you like, what you can think, since this is rather abstract, is just, at each site, independently of all other sites, add something that depends upon a Markov process. Put a circular Brownian motion attached, independent circular Brownian motions attached to each site, and take the real part of the position. That's a good example of something that's like this. So, and I need here a gap condition. In other words, on the generator of the process. In other words, I have an invariant measure, and I need to know that I return to that invariant measure exponentially fast. I have exponential return to equilibrium. Okay? So they're very nice conditions, but they're also ones that are easy to verify for a wide class of things that one can write down. Okay, and under those circumstances, so let's let psi t solve 2 with psi 0, a delta function at 0. And then let's look at then the diffusion constant, which is the limit as t tends to infinity of 1 over t, sum over x squared, expectation value of psi t of x squared, where now expectation denotes averaging with respect to omega as well as the paths of this Markov process, and while we're at it, the distribution of the initial values of the Markov process with respect to the invariant measure. So averaging over all the noise that we have, this limit exists and satisfies that the diffusion constant, okay? So in this case, actually it's somewhat natural. Well, actually, no, I don't have to say that. Hold on. The diffusion constant is equal to delta g squared plus little o of g squared with 0 less than delta less than infinity. I have an upper bound, but it's not as nice looking and natural as the one that came out here. It does involve the localization length, but also some other stuff that I can't say much about except for it's finite. Incidentally, the c that sits here is the same c, by the way, that sits here. So I mean, the upper bound is really completely, this bound here was actually completely,
F1 is 2.
2 is this equation here. Sorry, can you even see that? It's this time-dependent Schrodinger.
I didn't see the 2.
Yes. Okay, so again, we have diffusion with a slightly different dependence on the coupling constant, but actually it's correct just because, right, in this case, you can check that the first order effect of this is 0 because the mean value of the potential does nothing, because it simply shifts. Of course, there should be an I here. It shifts by a random phase. We might as well actually assume the thing is mean 0, because the effect of adding a random, multiplying the wave function by an overall phase has no effect on the modulus squared. So it's only the second order that it has an effect, and it does have an effect to second order, is the point. And again, everything up to here doesn't depend upon localization. To go from here to there, I need localization. So in this case, if lambda is equal to 0, then d of g, I should have checked this, is at least, I'm not sure it's equal in this case.
So Jeff, the existence of
Yeah.
the limit comes just from the heat path.
Yes.
The first one.
Okay, so in this case, the diffusion constant blows up as g goes to 0 if I take lambda equals 0. Okay. So now, in fact, the two proofs of these things are remarkably similar, and they use essentially the same structure. In fact, this one is somewhat simpler, even though this one, it involves this sort of thing that is less familiar to many, namely the Lindblad operator. But so let me say, well, actually, I'm supposed to stop, but I wanted to say a few words about the proof, but I'm not sure I should, because I'm supposed to offer time for questions, and I have exactly 7 minutes left. So, well, I guess I'll simply say the following about the proof. So that the basic outline of the proof is that it uses an idea which can be traced back to the probability literature in discussions of random walk in a random environment. Namely, what we do is we consider, in some sense, the environment from the standpoint of the particle. And the way that can be done here, because the particle satisfies a wave equation, so one can do that very precisely for random walk in a suitable type of random environment. Namely, you just simply, the particle itself is doing some position hopping process, and you simply center yourself at the particle and look at what the environment looks like. For us, we have something that satisfies a wave equation, but what can be done is that you consider the problem on the space of Hilbert-Schmidt operators. That's where the density matrix sort of lies, and we can restrict our attentions to Hilbert-Schmidt density matrices, together with the disorder space. And in this case, one has to also include the dynamical random variables, but let's focus on the first theorem. So this is going to be some Hilbert space that we're concerned with. And then the expectation of, say, rho t xx, I changed notation on you. This should have been something else. I should have used Dirac notation for that. Is the following. It's the inner product of rho t with a delta function at x tensored with a delta function at x. That's telling me to take the XX matrix element, together with something that's constant with respect to the disorder. And then there's a semigroup that sits here that is precisely the semigroup generated by commutator with h omega and add g times L acting on the initial condition. So at this point, all I've done is I've said, hey, I can write expectation as inner product with the function that's constant equal to 1. Okay, and I can rewrite matrix elements in a very funny way. But the point is that on this space, I can now introduce a Fourier transform. And so that this actually turns into the integral with respect to k of e to the I k dot x of something, which actually takes a particular form. There's a fixed vector, well, this operator has a Fourier transform that fibers over k. That has to do with the translation invariance assumption. And this inner product is now taken over a smaller Hilbert space. This is now in L2 of ZD tensor L2 of omega. So in some sense, what we've done is we've got rid of one of our position variables, which you can think of as the position of the particle. Unfortunately, because we have to consider the density matrix, we still have this other thing, which is sort of how far off the diagonal of the density matrix we're looking. But you notice I'm looking 0 off the diagonal here because I have XX and 0, 0. And then, in some sense, this thing's generating the evolution in quantum mechanics of the environment with respect to the position of the particle. And OK, so from here, things turn into a spectral analysis of this generator. And I don't have time to say more. But the fundamental idea is that the translation invariance of this equation in distribution translates to an actual translation with invariance of this with respect to a suitable group representation of ZD here. And let's just do some Fourier analysis, which then turns the thing into a spectral problem for a particular non-self-adjoint operator, but it's one that's dissipative. It has its spectrum in the right half plane, and it's one that one can perform under the hypotheses I've given. OK, so I'll stop and take questions.
Comments?
I don't understand how you get the limit.
Okay.
Go ahead.
And on model number 2, if G is, of course, non-zero, I thought, for example, if you just had the Laplacian, you proved diffusive motion.
Yes, yes, yes.
Right? So
Right.
I mean, don't you always get diffusion if the
You
rate
do.
of potential is bounded, right?
Right, you do. You always get diffusion.
Right.
I mean, I'm focusing on what happens in the large disorder regime at weak coupling because that's sort of the new result. But yes, the omega here is actually completely unimportant, but it affects the estimate that one gets. If you have large disorder, then you get this very small diffusion constant. Yeah.
Yeah. So, so do you see any chance of attacking the Anderson delocalization problem in 3 and higher dimensions by taking G to 0 and seeing that diffusion constant does not go to infinity?
Did you read my NSF proposal? This is the kind of crazy thing that one claims. In some sense, yes, I see a chance, but in some sense, right, there's a it's not going to be easy. Okay, these methods are at their heart very soft, and in order to do that, you're going to have to prove some really hard estimates. But you do have the advantage that at least you're trying to, you can imagine doing it perturbatively because you're trying to perturb from a system that has the right qualitative behavior. So in some sense, you can set the problem up, right? You have a diffusion constant. And, okay, but it's not simple. And whether that's going to be the way that someone does it is unclear to me.
So typically if you have a linear coupling between the small system and bass, I would expect diffusion to be proportional to G squared, right? So for instance, if you look at Davis Spohn or things like that.
Yeah, I think the G that sits here, yeah, the G that sits here is probably G squared from the original equation. Yes, because right. Yeah, there's sort of, I think when you compute that, the bath comes in here twice. You get, this term always, this Lindblad always comes, it comes out of ladder diagrams in perturbation theory, and it's always basically this sum. It's always this. And so it's, right, and these represent interactions with the bath. So there are two bath operators here. So this G is a G squared. That's, yes.
And then probably also explain why you expect your Lindbladian have some quadratic behavior, right? Because of this, even if it's linear relation between the bath and the small system, because it appears twice, it's like quadratic, right?
Yes.
Other questions?
Yeah, Jeff, the existence of the limit seems to be, let's say, the first model property of the heat bath somehow. Or the Lindblad has nothing to do with the operation.
Yes, exactly. It has very little to do with H. Although the proof needs is some translation invariance. So I need to be able to do this part of the proof, to take a Fourier transform. And so I need some way to have my H omega living on some space where I can have a group of translations that commute with it.
How are you getting the limit after that?
Well, okay, how do I get the limit after this?
Do you want a bag lemma? No.
No. I mean, I ran out of time, and so right, I want the diffusion constant, so I have to take the, what I need is what I need from this, I need to take the second derivative with respect to k and set k equal to 0. So I end up, so I need the second derivative of this guy with respect to k equal to 0, right? So if I take derivative of this with respect to k, I get the x squared, move it over here by integration by parts, so I get second derivative of this. And I do this, I use, a formula for differentiating a semigroup, and I get an expression. And some of those terms, so the k equals 0 term, actually, this is an eigenvalue with eigenvalue 0 for k equals 0. So there's actually just one particular term that contributes. And then I need to do basically a resolvent analysis of g hat 0 near energy 0.
And where do you use localization?
Localization is done then after you've established that in estimating, so you compare, you do a perturbation theory of the resolvent that gives you the diffusion constant and what you get when g is equal to 0, where localization tells you get 0 for the answer, because the whole method works at lambda equals 0. And since by other means...
It's used to control the error.
Yes.
Right?
Yes.
Other questions? If not, two things. First of all, let's thank the speaker again.